All right. Here in this video, we will see continuous random variables and some distributions. First, we need to define what a continuous random variable is. I'm going to give you a definition, and then I will try to state the main differences between the continuous distribution and a discrete distribution, or a continuous random variable and a discrete random variable. First, a random variable is said to be continuous if its PDF, probability density function, given by f of x satisfies that the probability that A is less or equal than B, the probability that A is less or equal than X and that X is less or equal than B can be computed by means of a definite integral, the integral from A up to B of f of x dx. For any two real numbers A and B. So here we have probability density function to define or to distinguish when a random variable is continuous. The main issue we have here, the main feature we have here is that when we compute probabilities for continuous random variables, we do it by using its PDF, and its PDF is used at the same time by using an integral. So we have to use a definite integral to compute the probabilities for continuous random variables. And of course, with this we have certain definitions or certain properties. First, from this definition, notice if x is continuous, then the probability that x is exactly equal to A is the same as the probability that x is between A and A. So from the definition, This probability is only the integral from a up to a of f of x dx. But this integral always is 0. So in other words, the probability that x is exactly any number for the continuous case is 0. Yeah, this is one characteristic for continuous random variables. The probability they take exactly one number, exactly one value, that probability is always 0. This is a big difference, right, with respect to the discrete case. In the discrete case, we can have cases when the probability that x is equal to one specific number might be not 0. But in the continuous case, always it's going to be 0. The probability that x is equal to exactly one value is 0. Other thing, remember that the integral, the definite integral, if f of x is a positive function, the definite integral can be interpreted as the area under the curve. So in the continuous case, yes, this only the area is equal to the probability that x is between a and b. So this area is equivalent to probability. So yes, when we compute in the continuous case, well, it could be also in the discrete case, but especially in the continuous case, I think it's good to remember that probabilities is going to be equivalent to computing areas under the curve for a given function. Yeah, it's going to be convenient to think in that way. What else? For any PDF, the probability, f of x should be greater or equal than 0 for any x. And number 2, the integral from negative infinity up to infinity of f of x dx must be equal to 1. These are two properties of the probability density function. PDF probability density function. All right. So I want to mention the main differences. But before I do that, let me talk about the cumulative distribution functions. The CDF, that is cumulative distribution function of a continuous random variable x is the same as in the discrete case. It's denoted by capital F. F of x is the probability that the random variable is less or equal than that x, and in this case is computed as what? The integral from, well, I can use some other symbol, for example, a a is the probability that the x is less or equal than any number a. So some basic formulas. For CDF, we have two. First, the probability that x is greater than a is 1 minus f of a. And the probability that a less or equal than x less or equal than b is given by f of b minus f of a. So these formulas, I mean, all of these formulas, of course, we're going to need them later. Oh, we can also define expected values. Expected value for the continuous case is given in this way. The expected value of x is the integral of negative infinity up to infinity. Remember that for the discrete case, we had to multiply x times the probability mass function. It is the same here, but in the discrete case, we have to do a sum. Here, we have to multiply and compute the integral. And of course, we can also define the variance that is given by expected value of x squared minus expected value of x raised to the square. So again, we're going to be needing all of these formulas later. But by now, I want to point out some differences. Some differences between discrete and continuous random variables. Discrete random variable. We can say that models problems involving outcomes you can count. For example, number of heads, number of tickets, and so on. So that is one way to try to distinguish or try to understand that we have a discrete random variable. When we have something that when all the possible outcomes, it's something that we can count or enumerate. Its probability density, probability function is called PMF, probability mass function. And it satisfies f of x I should be greater or equal than 0 for any x1, x2, and so on. The sum over this xi should be equal to 1. And one very important characteristic is the probability that x is less or equal than a in general is different from the probability that x is less than a. This is for the discrete case. What about for the continuous case? A continuous random variable, in general, we can say that models problems whose outcomes can be any number inside an interval. Of real numbers. Interval like a closed interval or an open interval, or actually all the real numbers, etc. Its probability function is called PDF, probability density function. Probability density function. And remember that unlike the case of discrete case, here we use integrals. The integral of f of x dx over all the real numbers should be equal to 1 to say we have a valid PDF. And here The probability that x is less or equal than a is the same as the probability that x is less than a. This is a very important and big difference. Notice, for the discrete case, the probability that, in general, the probability that x is less or equal than a is different than the probability that x is strictly less than a. This happens for the discrete case. For the continuous case, it's the same. The probability that x is less or equal than a is exactly the same as the probability that x is strictly less than a. That is a very big difference between the discrete random variable and the continuous random variable. All right. So these are only some important and main characteristics. All of this. So with all of this at hand, now let's try to see some examples to apply all of this. All right, this is one example from Webwork. It says the continuous random variable x has cumulative distribution function given by f of x. Notice we are being given this function, the cumulative f of x, and it defines 0 for any x negative. For between 0 and 2 is x minus 1 over 4 x squared, and for any x greater than 2 is only 1. So in this case, we'll focus only on this part to get the probability density function. How do we do that? Well, something that I didn't mention, but it is based on the definition. If you have the f of x in the cumulative, if you compute the derivative for the cumulative, you will get the PDF. So when you are given the cumulative and you find the derivative, you will get the probability density function. So in this case, before I respond to the questions I have here, let's find the PDF. Here, since the CDF is f of x, notice how this is only, we can focus only on this part, this one, because for any x less than 0 is negative. For any x negative, the cumulative is 0, and for any x greater than 2 is 1. So I can focus only the part from 0 up to 2. For 0 up to 2, the CDF is x minus 1/4 x squared. So you compute the derivative, you will get the CDF, the PDF, I'm sorry. That is only 1 minus x divided by 2. Find the derivative. If you have the derivative, now we can verify that this is actually a PDF. How can we verify that? One property that I have mentioned before is that the integral over all the real numbers for the PDF should be equal to 1. Here, this is an important property. To have a valid PDF, the function should be great. The values of the function should be positive or 0. But the other important property is that the integral over all the real numbers for the function should be equal to 1. So we can verify that for our example. Verifying it is a valid PDF. How do we do that? We have to compute the integral from negative infinity up to infinity of the PDF. But notice, in this case, for this example, our PDF is only valid from 0 up to 2, so I can ignore all the other numbers. So in this case, it's going to be the integral from 0 up to 2 of 1 minus x divided by 2 dx. See that? And then use your knowledge from integrals. This is going to be x minus x squared divided by 2 times 2 is 4, evaluated from 0 up to 2. And this is going to be only, note, since I have 0 here in the bottom, when I substitute 0 here and here, it's going to be only 0. So I can focus only on the 2. This is going to be 2 minus 2 squared divided by 4. And this is only 2 minus 1, that is 1. See that? So yes, this is a valid PDF because the function is going to be positive and the integral over all the other numbers, that in this case is reduced only to 0 up to 2, is 1. Now, let's respond to the question that we have here. First, the part A, it says, part A, 2 independent observations of x are taken. Find the probability correct to 2 decimal places that one is less than 1/2 and the other one is greater than 1/2. Well, so far we haven't seen how to compute probabilities of random variables when they are independent. I haven't defined that. We're going to do that later. So by now, if you see this problem, if you see this question, you can enter this answer. Yeah? So don't worry about this precise question. If you can skip that part, well, you want to get the right answer, only type the answer. But I'm going to focus on the rest of the problems. First, part B. Part B says find the expected value of the square root of x. In this case, we will have to use a formula that is similar to the one for the discrete case. If h is a function, then the expected value of h of x is defined as the integral from negative infinity up to infinity of h of x times f of x dx. So in this case, the function that is being applied to x is the square root. So I have to compute the integral from negative infinity up to infinity of the square root of x times f of x dx. But in this case, f of x is only this, 1 minus x over 2. So I have the integral from 0 up to 2 of the square root of x times 1 minus x over 2 dx. And this is going to be the integral from 0 up to 2 of the square root of x minus square root of x times x is the square root of x raised to the, oh well, it's going to be x raised to the 3 over 2 divided by 2 dx. And now apply the integrals, the formula for integrals. This is going to be, you can use the power rule for integrals to compute this. Remember that the square root of x is like x raised to the 1/2. So it's going to be x to the 1/2 plus 1 is 3 over 2 divided by 3 over 2. That is going to be 2 over 3. 2 times x divided by 3. Minus, here 3 over, here I have to add 1. 3 over 2 plus 1 is 3 halves plus 2 halves is 5. So 5 raised to the 2, 5 raised to the 5 over 2 divided by 5 over 2, that is in the end 2 divided by 5. Evaluated from 0 up to 2. Remember here, I'm using this formula. The integral of x raised to the n dx is x raised to the n plus 1 divided by n plus 1. The power rule for integration. And then you have to, oh, I'm sorry. This is correct, but I forgot this too. Don't forget it. So it's going to be 5 times 2 is going to be 10. So you need to evaluate this, and you are going to get, if you do the operations, you will get 4 times 2 raised to the 5 over 2 divided by 30. And this is going to be approximately the answer you see here, 0.75. You can verify that. Okay? Part B. Part C. Part C is asking for what? The expected value. The common expected value. The common expected value is, by definition, the expected value of x is the integral of negative infinity up to infinity of x times f of x dx. But it's only the integral from 0 up to 2 because the PDF is valid only on this interval of x times 1 minus x divided by 2 dx. And this is only the integral from 0 up to 2 of x minus x squared divided by 2 dx. And this is going to lead to two integrals. Again, apply the power rule. This is going to be x squared divided by 2 minus x raised to the 3 divided by 3 times 2, that is 6, evaluated from 0 up to 2. And then this is going to be, notice again, remember you have, when you are evaluating a definite integral, you have to evaluate first the upper limit, wherever you see the x, and then minus, evaluate the lower limit. But since the lower limit is 0, this is going to be 0, 0, so I can focus only on the upper limit because this is going to be 0. So it's going to be 2 squared divided by 2 minus 2 cubed divided by 6. And this is going to be only 4 divided by 2 minus 8 divided by 6. And this is only 2 minus 8 over 6. Or what it is saying, 4 divided by 6. Or what it is saying, approximately should be 0.67. 0.67. So the answer is correct. So part B, part C, part D. To find the part D, you will have to use the variance of x. The variance of x, remember, is computed you can compute it with this formula. The variance of x is this one. You will have to compute the expected value of x squared minus the expected value of x raised to the square. The expected value of x, you already have it, is 0.67. Raise that to the square, but first and subtract from what you get from expected value of x squared. How can you compute this? Well, you will have to do the same I did here, but you will have to, instead of putting the x here only, you will have to put the x squared. Okay, so to compute the part D, you will have to use this formula. But you have, anyway, you have the answer. The answer is this one. Should be 0.22. Should be this. Now, find the median of x. The part E. The part E is find the median. The median of a random variable x is defined as the value m0 such that the cumulative evaluated at m0 is equal to 1/2. That is the definition for the median. It's like the point that is exactly in the middle, such that we have 50% of the total values of the random variable to the left and 50% to the right. But here we have to compute the median. So how do we proceed? Well, use the definition. Start with this equation, f of f0 equal to 1/2. So we have f of f0 is equal to the integral, in this case, in our problem, from 0 up to m0. Remember, this is the cumulative. I have defined this function. The cumulative is this. It is CDF. F of A, probability of x greater or equal than A, is from negative infinity up to A. Probability that x is lesser or equal than m0. Or the integral from, should be negative infinity up to A, but in this case the lower bound for this one is only 0, so 0 up to m0 of the function f of x. That in this case the density is 1 minus x over 2 dx. The point here is that we have to find the value for m0 such that this integral is equal to 1/2, because that is the definition for this. So compute the integral. As you know, this is going to be the integral of x minus x squared divided by 2, that is 4, 2 times 2 is 4, evaluated from 0 up to m0. And that is going to be equal to 1/2. Next, this is going to be, again, the same as before. When you substitute the 0 here, it's going to be 0, so focus on the upper limit. It's going to be m0 minus m0 squared divided by 4 equal to 1/2. And then you have this. You're going to end up with a quadratic equation. If you manipulate this, you will have m0 squared. Oh, well, first, I'm sorry. I think we can multiply first both sides by 4. So we can cancel this 4. It's going to be 4 times m0. This is equivalent to 4m0 minus m0 squared equal to 4 divided by 2 is 2. So we have a quadratic formula, right? A quadratic equation. If we simplify this, we're going to have m0 squared minus 4m0 minus 2 equal to 0. Quadratic equation. So this can be simplified you will have to use the quadratic formula for this. Okay? If you use the quadratic formula, you will get two values, but the value you should get is this one, 0.59. When you solve this equation, when you solve it, you will have two values, but the value that is the correct should be 0.59. Why 0.59? Because should be a value between 0 and 2, right? The other value that you will get is going to be outside 0 and 2, so it has to be any value between 0 and 2. Do this, and you will get m0 equal to approximately 0.59. All right. And so, oh, I'm sorry. I think I did a mistake here. M0, this, you cancel this adding. No, this is correct. But you cancel this adding. So I'm sorry. It should be plus. Yeah, I'm sorry for this mistake. Anyway, when you do it, you're supposed to get this answer. All right. The other one. So we have the part E. Finally, part F. The part F is asking for find the value of C correct such that you have this equation true. So we have expected value of x plus C equal to 4 expected value of x minus C. And remember, what we already have the value for the expected value. So in this case, we can use the properties for expected value. Expected value of a sum is only the sum of the expected values. So this is the left-hand side of the equation becomes expected value of x plus expected value of c. And the same for the right-hand side. I forgot the expected value. Yeah. So this is going to be only 4 times expected value of x minus expected value of c. Now, the expected value for a constant is going to be only the constant. So in this case, we have expected value of x plus c equal to 4 times the expected value of x minus c. And in this case, you have to solve only for c. So this becomes expected value of x plus c equal to 4 times expected value of x minus 4c. So do the algebra operation here, and this is going to be 5c equal to 3 expected value of x. And with this, you will have use the value for the expected value. Expected value of x, we computed it before. Expected value of x, here you have it, is 4 over 6 or 2 over 3, right? It's going to be 5c is equal to 3 times 2 over 3. So we have c is equal to, here we can cancel the 3 with the 3. What is left? Only 2. 2 divided by 5. Two divided by 5. So it should be 0.4. Yeah, and it is, right? Point 4. Very well. And with this, we complete the part F. Again, ignore the part A. Only copy the answer. Yeah? You don't have to do it. Part A, copy this answer. Focus on the other exercises. All right, now additional examples or additional exercises. Sub-exercises. For this exercise is what about, for example, you want to compute the probability that x is greater than 1. Well, in this case, you have two ways to do it. You can do the PDF. I mean, set up the integral. In the integral of what is the lower bound for this, or where this function is defined? It defined from 0 up to 2. Yeah, from 0 up to 2. The PDF. So you want to arrive up to 1. Then this is 0. No, I'm sorry. In this case, it's greater than 1. So you have to put 1 at the lower limit and up to the upper limit, that is 2, of f of x dx. Or you can do it in this way. You will have the same value as, well, let me do it. This integral is the integral from 1 up to 2 of 1 minus x divided by 2 dx. And this is the integral of x minus x squared divided by 4 evaluated from 1 up to 2. And in this case, we will have to take into account the lower limit because it's 1, right? So this is going to be 2 minus 2 squared divided by 4 minus 1 minus 1 squared divided by 4. And this becomes 2 minus 1 minus 1 minus 1/4. And this is only 1 minus 3 over 4. And 1 minus 3 over 4 is only 1/4. This should be the answer. The probability that x is greater than 1. But other easier way to compute this is directly with the CDF. Probability that x is greater than 1, use the formula we have that I gave you before. This one, probability that x is greater than a is 1 minus the CDF evaluated at a. So you already have the CDF, then you can use it. I mean, it's going to be 1 minus f of 1. The CDF is the formula given directly. This one. X minus 1/4 x squared. So it will be 1 minus x evaluated at 1, 1 minus 1 squared divided by 4. And you will realize that this is going to be 1 minus 1 plus 1 over 4, and this is only 1/4. That is the same we obtained here, you see? So it's the same. This way, or this way, of course, we have the same results. If you don't have the CDF, then you will have to use the density. But if you already have the CDF and you want to compute probabilities, I recommend to use the CDF. Okay? All right. Now, let's see some continuous distributions. In the discrete case, remember that we categorize distributions by means of their PMF. I mean, the formula that defines or gives you the probabilities. We use those functions or formulas to distinguish or to classify random variables. Well, we have the same here. The formula or the function or the PMF is going to determine or define a given continuous random variable. The first one is uniform distribution. And we say a random variable x has uniform distribution if its PDF is f of x equal to 1 over b minus a for any x between a and b, where a and b are any real numbers. So in this case, this is the maybe the easiest continuous distribution. It's only defined by a constant. You want to compute the probability that a given random variable falls in any value of for a given interval from A up to B, then you can use the uniform distribution. For example, suppose that the random variable x is uniformly distributed between 4 and 28. So here in this case, A is equal to 4 and B is equal to 28. Draw a graph of the density function and then use it to help find the following probabilities. Well, we don't need to do the graph, but you want to do it. It's only a constant function, f of x is equal to 1 over b minus a. That is only 1 over 28 minus 4. What is the same? 1 over 24. So you want to do a graph for this. It's only the function at 1 over 24, a constant function, is this, but only from 4 up to 28. 4, let's say that here the 4, and here the 28. This is not the right scale, it's only representative. There you have. So we can, if you compute the area for this rectangle created in this way, you realize that the area is 1. Well, the point is how we can compute the corresponding probabilities. All right, for example, the first one, greater than 28. Probability that x is greater than 28. Again, you have to set up, in this case, we don't have the cumulative. We have to set up the integral. So this integral is going to be the integral from where? This, in this case, notice, what is the lower limit for this? According to the definition, it defines only from A up to B. So in this case, A is 4 and B is 28. So greater than 28 has to be, well, has to be from A has to be from 28 up to 28. Give me a second, please. Yeah. In this case, pay attention to this. It is from 28 and onward. So 28, so you start with 28. And you have to put it with the limit, this is lower limit, and the upper limit has to be the value of b, that is 28. 28 up to 28 of the function f of x, and in this case it's only 1 over 24. 1 over 24 dx. But in this case it's going to be only is going to be, what did I say before? That this integral is only what? When you have the same point in the lower limit and the upper limit, this integral is automatically 0. So we cannot observe a value greater than 28 for this continuous random variable. So the answer here is 0. What about less than 9.1? Part B, less than 9.1. Less than 9.1. In this case, we want 9.1 less. So this has to be the integral from 9.1, the upper limit should be 9.1 or less. But the less has to be determined by what? By the value of a, that is 4. So it's an integral from 9.1 up to 4. 4 up to 9.1 of f of x, but f of x is only 1 over 24 dx. And this only 1 over 24 is a constant, so it's 1 over 24, the integral of 4 up to 9.1 dx. And this only 1 over 24 times x evaluated from 4 up to 9.1. But this is only what? This is only 1 over 24 times 9.1 minus 4. And this is only 5.1 over 24. That is approximately, well, no, it's exactly in decimals 0.2125. So that should be the answer we have there. 0.2125. And so on. What about for the other one? For between 7 and 25. So in this case, set up directly the integral. Part C, probability between 7 and 25. It's only the integral from the lower limit 7 up to 25 of 1 over 24 dx. And repeat the process. This is take out the constant 1 over 24 of x evaluated from 7 up to 25, and this is only 1 over 24 times 25 minus 7, and this is only 18 over 24. And you can verify that this is going to be 3 over 4. This is divided by 6, both. 18 divided by 6 is 3, 24 divided by 6 is 4, or 0.75. And in the same way, you can do this one. Yeah, by the way, you want the answer is this, 0.583, 33333. But you do it. You do the part D. We have to complete this one. Yeah, anyway, the answer is this. All right. So, we have seen the uniform. Other one. exponential distribution. And in the same way as we did it here, it's going to be defined by what? By means of its PDF. A random variable x has an exponential distribution if its PDF is given by f of x equal to lambda times e raised to the negative lambda x for any x positive and 0 elsewhere. This distribution is very important in many applications. So I will write down some important applications. Well, in general, an application. This random variable is useful to model the probability distribution of the elapsed time between two successive events. So the elapsed time between two successive events, you want to know the probability that the time is a given is a particular value, then you can use this distribution. We're going to see one example. But again, notice how it is determined by its formula. Here, expected value for this variable is 1 over this symbol. This symbol, by the way, is lambda, the Greek letter, lowercase Greek letter lambda. We have it here, and we have it here. And notice, yes, this is the number e. So this is exponential function raised to the negative lambda times x, where x is the variable. If you compute the expected value for this, you will have 1 over lambda. And by the way, you want to know the variance for this random variable is 1 over lambda raised to the square. The cumulative is given by 0 if x is negative, and 1 minus e raised to the negative lambda x if x is greater or equal to 0. So let's see one example for this exponential distribution. So it says a bank wishing to increase its customer base advertises that it has the fastest service and that virtually all of its customers are served in less than 9 minutes. This is what they claim. 9 minutes. A management scientist has studied the service times and concluded that service times are exponentially distributed with a mean of 4.5 minutes. Determine what the bank means when it claims virtually all its customers are served in under 9 minutes. And then we have to look for the proportion of customers served in under 9 minutes. So in this case, X what is X in this context? Service time. Service times. And we know that the distribution with respect to probability for this time is exponentially distributed. So it has a function like this form. The mean or the expected value is 4.5. So based on this, since the mean is 1 over lambda, 1 over lambda is the expected value, or the mean, then 1 over lambda should be equal to 4.5. Use this to compute lambda. Lambda is equal to 1 over 4.5. Or what is the same? Four 0.222222. Then the question is determine what the bank means that when it claims virtually all its customers are serving under 9 minutes. So we look for the probability that the service time is less than 9 minutes. So probability of X less than 9. In this case, you can use this cumulative. But if you want to do it, if you want to use something better, I recommend to use the application that we use for the discrete case. For the discrete case, this is the application. Probability distributions. So identify exponential should be here. Exponential is the third row. Exponential. Click there. And notice, to use this, you will have to specify the value of lambda first. Lambda is 0.222222, as many 2's you can use. Specify the value of X. The value of X is given by 9 in this case. So type 9. And what do we want? Probability of less or greater. In this case, it's less. So type less. And type done. Well, in this case in Spanish, aceptar. But it's done or enter. And the probability is 0.864665. Point 86465. 4665. And you can verify this is the right answer, right? Because it's this one. That okay? So I recommend to use that application if you want to compute problems like this. But of course, we have to understand what you're using and why you can use that. In this case, only because it said directly that this random variable is model can be modeled with an exponential distribution. Oh, sorry. One more distribution. Very important. This is going to be the normal distribution. Normal distribution. And again, we will define this by using its PDF. A random variable x has a normal distribution if its PDF is given by f of x equal to 1 over sigma times square root of 2 pi times the exponential function raised to the negative 1/2 of x minus mu divided by sigma raised to the square for any real number. This distribution is valid for any real number. This symbol is the Greek letter mu, but actually it is the expected value. This mu is the expected value of x. The mean of a normal distribution is denoted by mu, and sigma squared is the variance. By the way, if you compute the square root of the variance, you will have something called the standard deviation. There you have. When you are dealing with normal distributions, all of these numbers, the mean, the variance, and standard deviation are very, very important. What else? Since this is a very important distribution, I want to talk about many properties. First, graphically, if you do the graph for this function, the normal distribution has this form. It's like a bell. The graph of the distribution is like a bell, or bell-shaped. In the middle, always you will have the value of the mean, mu, always is here. All the area, this curve goes along all the real numbers. And if you compute the area for this, all the area under the curve, all this area, all the possible area, this area is the integral from negative infinity up to infinity of f of x dx. And of course, since this is about the PDF, this area, this number, or this area is equal to 1. So in other words, the probability that x is between any value or is any value in the real numbers, this is 1. And again, here in the middle, we can say that we have the value of the mean. And we can say that it divides this into two parts. Values after the mean and values behind the mean. And it divides this exactly. more properties. The probability that a normal random variable is between A and B is again the area under the curve. So you have two numbers, A and B. When you are computing the probabilities between A and B, you are computing this area. So the area is equal to this probability. And the probability, this is property number A, property part B, property part C. Other very important property is that the distribution is symmetric with respect to the mean. That means that the probability that x is less than the mean is the same as the probability that x is greater than the mean. And this probability is equal to 0.50. So in other words, the probability of the area under the curve after the mean always is 1/2 or 0.50. And the probability or the area under the curve behind the mean is 0.50. This divides this curve into two parts that they have the same area, 0.50 and 0.50. And any normal graph distribution is symmetric with respect to the vertical line passing through the mean. This is, we can say that if we have the normal distribution, if you focus on the mean mu, then here in the middle, we have the mean mu. It means that if C is positive, then if you create the area, the region mu minus C and the region mu plus C, so for any C positive, this area is the same as the other area. The yellow area is the same as the pink area. So this can be written as the probability that x is between mu minus C and mu is exactly the same as the probability that x is between mu and mu plus c. Yeah, this is because the vertical line passing through the mean is symmetric. The normal distribution is symmetric to respect to its vertical line passing through the mean. We can say that if you draw a vertical line passing through the mean, we can say that the whole area is divided into two parts. You can say like this vertical line is like a mirror for the other part. And of course, here's something important, is that cumulative. We don't have a precise formula for the cumulative. But this is given by the probability that x is less or equal than a equal to capital F of a. Usually in some books it is denoted by this symbol. But it means only this. Yeah. And beside that, we have a very special random variable, normal random variable that is called the standard normal. Standard normal. The standard normal is defined as if C is a random variable with normal distribution with mean equal to 0 and sigma equal to 1, then C is called the standard normal distribution. Standard normal distribution. It has its special symbol, right? It is denoted by C. So when you see C and you're talking about probabilities, it is very likely that we're talking about the standard normal distribution. Actually, we can use the standard normal distribution to compute any probability related to any common normal distribution that is not normal. But we're not seeing here because we're going to be computing probabilities by using software or on an application. Oh, well. So let's see some examples. It says, suppose that the x is normally distributed. Example. X is normally distributed with mean of 100. Usually when you have to compute probabilities for normal distributions, you are going to be given the mean and the standard deviation, like in this case, mean and the standard deviation. What is the probability that x is greater than 118.2? Formally, you will have to compute that. You will have to compute the integral for this. Yeah, for this function. It might be very, very complicated, but don't worry. In this case, we can take advantage of the application that I recommended. So for the part A, we look for the probability that x is greater than 118.2. So go to the application that I recommended, or you find other one, no problem. Look for the normal distribution. Normal, you see, is almost in the middle. Normal. And here you will have to specify the mu and sigma, the mean and the standard deviation. In our problem, the mean is 100, mu is equal to 100, and sigma is equal to 14. So type those values here, 100 and 14. And x is, in this case, 118.2. And we look for the probability greater. Okay. 0.0, can see the value. One 118.2. 0.096800. 0.096800. That is this. You see? .6800. This is the answer. Now, in the part B, the question is slightly different. What value of x does only the top 13% exceed? In this case, we look for, when you have problems related to normal distributions, you can have typically two problems. The first one is, given a number for x, what is the proportion or the percentile or the percentage? The proportion or percentage or the area under the curve. It is. You're given one value of x, you find the probability, the percentage, or the area. The other type of problem is you are given a percentage, you have to find the value of x that satisfies that. I forgot to do this, but well, first let me complete this problem. We look for a number that I'm going to call x0 such that the probability that x, notice it says exceed 13%. X is greater than x0 is equal to 0.13. You see, we look for x0 here. But we know that the probability after x, the area under the curve after x0 is 0.13. So again, go to the application. The mu and the sigma are the same. But here first, you have to specify the probability of x greater than x. In this case, is 0.13. And then type enter or done or aceptar. And notice, look at the value of x. We have 115.769. You have this value. $115.76946. Now, well, of course, you don't have to do it, but how to interpret the sketch here? For the part A, draw a normal distribution, a bell-shaped curve. And here, what we're doing here, put here in the middle the value of the mean, that is 100. And notice this value 118.2 is to the right of the mean. Let's say that is here, 118.2. What are we looking for here? The area after this value. The area after this value, 118.2. All of this area is equal to 0.096. 8004. For the part B, the same, draw a bell shape. Again, identify the mean, 100. And notice, we were looking for x0 such that the probability that x is greater than x0 is 0.13. And that value is 115. 0.76. And this area after this number is supposed to be 13%. Or 0.13. All right. Finally, one more example. This is very simple. Once you have understood how to do the application, notice in this case you have to find the probabilities only for the standard normal, for C. Remember that C has mu equal to 0 and sigma equal to 1. So you want to find these probabilities, use only the application. For example, for the first one, C between negative 0.19 and 1.64. Go to the application, type mu equal to 0, sigma equal to 1, and in O, here we will have to use a formula that I have mentioned before. Probability that C is between these numbers is the same as the probability of the right-hand limit that C is less or equal than 1.64 minus the probability that C is less or equal than negative 0.19. So I have to find two values first. So we'll do this here. Is equal to first for 1.64. 1.64. 0.949497. 0.949497 minus now the one for negative 0.19. Negative 0.19. Enter. 0.424655. Actually, yeah. Notice the application is giving to you the graph. 0.424655. 0.424655. And if you do the subtraction of these two, 0.949497 minus 0.424655. We're supposed to get the answer. And yes, you can verify that the answer you get is 0.524842. That, of course, is the same as this one. See? And you can complete the other one, the other exercises by using the application. Is that okay? Only remember that when we're talking about C, the mu is 0 and sigma 1. All right. See you in the next video.